basic aircraft systems, and that in itself is, I would say, pretty hefty lesson plan, as I'm sure most of you already know. So I tried to kind of break it up into the planes that we fly. I'm not sure if a majority of you fly the 150 or if you fly the Cherokee, but I tried to kind of provide information on both of those aircraft. So whether, no matter which one you're flying, you're getting some relevant information today. But, aircraft systems is some big, broad strokes. So, yeah, take it for what it is here, but it'll vary aircraft to aircraft. But yeah, if at any point, again, you have any questions, just feel free to interrupt me. We'll get started. So today I'm going to try and talk about all three of, kind of the big hitters for aircraft systems, which is going to be the power plant, which is going to be the engine and prop, airframe, which is going to pertain more to our fuel systems and electrical systems, and the instruments, which are, as you know, the pitot-static and vacuum systems for our flight instruments. So we'll see what we get through. It's like I said, it's kind of a lot. So yeah. But let's start off with the power plant. So lucky for you all, we've got some pretty basic power plant systems on our Cherokee and our Cessna. We're going to start with the Cessna here, and we're just going to talk about kind of some big hitters. And I got this straight out of the POH. I'm sure you all have access to the POH on the Girls Love to Fly website. I definitely recommend taking a look at either relevant one for the aircraft you're flying. It's kind of right in the beginning, first 2 pages. They've got the specifications of the aircraft, specifically engine and propeller. That's going to give you a really good idea of what we're working with here. So in Bluebell, we have a Continental O200 Alpha. So essentially what that means is that Continental is the engine manufacturer of the engine, and the O at the beginning stands for horizontally opposed. And essentially what horizontally opposed means is that instead of the cylinders firing up and down, they fire side to side. And the reason that aircraft designers originally went for a horizontally opposed design versus a standard V engine or kind of a block engine is, number one, because back in the day, like a radial or a V engine actually reduced visibility in the cockpit quite a bit because of kind of the way the engine was configured or just the way it took up a lot of space in the windshield. The horizontally opposed engine is also very lightweight and easy cooling, which is why we stuck with it even in modern aviation. Sometimes you will see other identifiers starting at the beginning of your engine. So if you've ever seen an I, like an IO, that typically means, well, it always means that it's an injected. So instead of being a carbureted engine like our 150 and 140 has, it would be a fuel injected engine. There's also a T, which is turbocharged. There's quite a few little add-on letters that you could see at the beginning, and that's just kind of telling you broad stroke specifications of the engine. Does that make sense? Any questions about that? Wonderful. Okay, and then the 200 stands for the cubic displacement of the engine. So typically, it'll be more like a decimal. So I think the 150 has about a 199.3 cubic displacement. And really all that means is the volumetric measurement of the cylinders, but that's not so important as just knowing it's a measurement of the engine. So we've got the O, horizontally opposed, 200 cubic inches, and then the A. So what does A mean? The A is kind of like, you can think of it of, if this is the make of engine, the A is the model. So the A, being that it's the first letter in the alphabet, is typically kind of the first variation of this engine. Or it could be variations of the engine. The A may signify a certain type of set of magnetos that this engine has on it, or a certain starter the engine may have on it, or it may just dignify the I guess you could say, the variation of engine. So if we have the O200 Bravo, it's a second variation of that engine. Does that make sense? Okay, wonderful. So as we talked about a little earlier, since we don't have that I in the beginning with the O, our engine on the 150 is carbureted. And what that means is that we have a carburetor. And that means as pilots, we have a little bit more direct control over our fuel air mixture going into the engine. Whereas with an injected engine, it's a little bit more digitized with the way that they program that fuel air mixture. So with the carburetor, as you all know, the mix, we've got two knobs in the cockpit. We've got the red mixture knob, which is our fuel air mixture, and then we've got our throttle, which is our power. Both of these things are affecting the carburetor. The mixture knob is affecting the amount of fuel that we're getting into our air ratio, essentially. And then our throttle is dictating how much of that fuel air mixture we want to kind of pump into the cylinder. So it's opening our gate from the carburetor into the cylinder. So it's dictating our power. And one last thing about the O200A is that we have a oil and air cooled system. And this is pretty common on small general aviation aircraft. I guess you could say the alternative to oil or air cooled would be coolant cooled. So like what we have in our car, in our radiator, that's coolant. And some aircraft are cooled that way. But in this case, we're just oil and air cooled. So our oil serves dual purpose to lubricate the cylinders, which also reduces heat because nobody likes a little metal on metal friction. That's not good. And then air cooled through the intake as well as various other openings in the cowl to air the engine. And while we're on the subject of oil, the Cessna 150, as you can see up here, has a capacity of 6 quarts. However, if most of you fly the 150, you know that she doesn't really like to stay at 6 quarts. She usually likes to linger more around 4.5 or 5, and that's completely fine. That's this oil capacity here, the 6 is kind of the maximum, and sometimes just with wear and tear, it likes to take a little bit less. So our minimum, it doesn't say in this POH, but our minimum would be 4, our maximum 6. Yeah, and with that, we'll just talk about the propeller briefly. Not too much of note here. We have just a standard 69-inch aluminum propeller, and 69 inches is the entire diameter of the propeller. So not just like middle to tip, because if you think about that, that would be a very, very long propeller. And it is a fixed pitch climb propeller. So what fixed pitch means is it just in contrast to variable pitch, which you can change inside of the cockpit. We would have 3 levers. We'd have a blue in addition to our black and red. On this aircraft, it is a fixed pitch, so we don't change the pitch of the propeller. And when we say a climb propeller, it means that it is set to be most favorable for climb conditions. Does anybody have an idea of why we might prefer a climb propeller over a cruise propeller specifically in Bluebell?
Maybe because we don't have the power to really get up there quickly, so we want to have more pitch so we can climb faster. Maybe.
Yeah, no, that's actually a great point. Is since we have a little bit less horsepower, we got 100 horsepower on Bluebell, it's going to be more advantageous for us to have a propeller that's going to aid us in the climb stage. And another reason for that is also because of the purpose of the aircraft. So there's no reason that, for say we couldn't put a cruise propeller on Bluebell, but if we think about most of the training that we do, it's really pattern work. And so it's going to be more advantageous for us to get that climb performance, especially because we are, slightly underpowered, than to get cruise performance, because we're doing most of our training in a kind of a climb descent setting. Okay. Do any of you have any questions about Bluebell's engine propeller system before we move on to the Cherokee? Okay. All right. So the Cherokee, if any of you have flown it, know that it is a little bit more powerful than the 150. We have 140 horsepower, and we have a Lycoming 0320 E2A. So now you kind of know the drill. Lycoming is, I guess, the Continental and Lycoming are really the two big names in engine manufacturing for general aviation. So most of the time you're going to be either flying a Continental or a Lycoming. So in this case, we've got one of both, which is great. So we got the Lycoming, which is just the manufacturer. We've got that O, which we know means, whoop, little sneak peek there, means that it is horizontally opposed. 320, which is our cubic inches, and then E2A. So we got a little bit more of a complicated add-on at the end here. And essentially what this one means in particular is in relation to some additional add-ons that the manufacturer had for this engine particularly. So again, you can think about it like if you're buying a car from off the lot, right? Brand new. And you went on the website and you got to choose all your, accessories. I want this engine and this suspension and this radio, so on and so forth. Essentially, that's what they're doing by slapping that E2A on the end, is saying, here's these modifications for this specific engine, not to be confused with the other engines that are also 0320 with different attachments. So there's that. And similarly to Bluebell, the is also carbureted and oil and cooled. Now, the difference here is going to be in our quart capacity. So as you can see up here, we have a 8-quart capacity. And again, you're unlikely to find the Cherokee at 8 quarts. You're probably going to be sitting more around 7.5 most of the time. And with our 8 at maximum, our 6 is going to be minimum here. And that's just due to a slightly larger engine displacement and more power. We're going to need more quarts. Same thing here with the propeller. Instead of our 69-inch, we're going to have 80-inch aluminum propeller. So they're made out of very similar materials. And once again, we have that fixed pitch climb prop. For the same reasons, we're just looking to maximize our power at the climb setting, since that's where we're going to be doing most of that training. And, these aircraft specifically, regardless of, we could put cruise props on here, but they were designed with pilot training in mind. So they just came with that climb propeller. All right. So that is engine and propeller. Before we move on to airframe, do any of you have any questions? Alrighty. Okay. Let's talk about airframe and let's talk about fuel specifically. So again, luckily, we have some pretty straightforward fuel systems, and actually in the Cessna and Piper, they are still pretty similar, but they have one or two definitive quirks. So we'll start off with Bluebell again. With the fuel capacity, we have 26 gallons capacity on each side, 22.5 usable. And because we have less usable, it's for that 30-minute day VFR minimums. So you can't go below 22.5 because that would put us into that illegal usage category. It takes 100 low lead and it burns about 5 gallons per hour. So that's pretty good. If we look here at the diagram, and let me know, can you all see the diagram okay?
Yes.
Perfect. Okay. Just want to make sure because I know sometimes quality doesn't come across the best in Zoom, so I want to make sure. Perfect. So if we look at the fuel diagram here, we've got our left fuel tank and our right fuel tank. And as we know, those are above us in the wings. So a big part about the Cessna fuel system is that it is partially gravity fed. And that makes sense, right? Because our tanks are sitting above us, fuel flows down into the engine. Now, inside the cabin, you know we have an on and an off switch. And some planes, and actually in the Cherokee, we can choose which tank we want to pull from. So we have left, right, and off. In Bluebell, we just got on and off. So you won't make it very far out of the chains if it's off. So we've got it on, hopefully. And it will feed between two tanks equally, allegedly. It's supposed to feed from both tanks equally. Now, sometimes you'll get a little more feed from one tank than the other. I don't know if any of you have experienced that personally, like on a cross country where, say the left tank is looking at about a quarter and maybe the right tank is looking, 3/4. That happens sometimes just due to the way that we're flying. If we're flying slightly wing low on one side, it may fuel favor draining from one side over the other. It will tend to equilibrate during flight, and this is also because it's kind of cropped out here, but on the left tank is the only tank with the vent, so it will tend to want to drain from that left tank over the right tank. So it will tend to want to come back to an equilibrium in flight. The other thing you can do is always do a steep turn to the side where it has less fuel if you wanted to kind of try and even out those tanks, but should be all right. So it comes through here on our fuel selector, goes through a fuel strainer, which is located in the engine compartment. So it's actually on the firewall. And then it goes into the carburetor, which, as we talked about before, is that fuel-air mixture, which is controlled by our mixture and throttle knob. And then it goes into our cylinders. So what this fuel system doesn't show that I really want to highlight is the engine-driven fuel pump. So in our Cessna, because it is gravity assist, we only have a engine-driven fuel pump. So that means that, theoretically, if our engine-driven fuel pump were to fail, most likely we're going to have an engine failure, which is why in the 140, it's nice that we have that backup electrical pump. So in the 140, again, since we've got a little bit more power, we're a little bit of a bigger airframe, we've got a higher carrying capacity for fuel. So we have, in fact, we have just about double. So we have a 50-gallon capacity, 48 usable, again, third reserve. Although at 8.5 gallons an hour, 2 gallons seems less than 30 minutes, but that's all right. That's what the POH said. So, and then the 140 has that electrical and engine-driven fuel pump because, we think about that Cherokee. It's got our tanks below the wings, so there's no gravity assist in that situation. So we need a way in order to get that fuel out of the tanks and up into the engine. Now, typically in straight and level flight, that engine-driven fuel pump will be enough. But in times where we may be excessively nose up or nose down, or potentially in a steep bank, right, when we're doing maneuvers or coming into land, or taking off for that matter, it can cause the fuel in the tanks to slosh, which can cause the engine-driven fuel pump to have a hard time pumping that fuel out on its own. So that's why we have that backup electrical pump, which is going to have easier access to the tanks, which is going to assist us during those times where that sloshing may, cause like a stutter in the engine, or worst case scenario, an engine failure. So that they installed that extra electric fuel pump for safety purposes. But if we look at the diagram for Cherokee, it's essentially the same ordeal. We have our two main tanks, left and right. We have our fuel tank selector valve, which, the only difference there is that we've got left, right, and off. And, we set that timer for every 30 minutes to change the tanks because we want to make sure we're flying balanced. Our fuel strainer here. Again, that engine bay. And then it comes and puts it right on into the carburetor, which is controlled by that mixture and throttle. So essentially, the only difference between the Piper and Cessna fuel system is, of course, one, the capacity, and two, that additional electric fuel pump on the Piper. But other than that, they're pretty similar. So, do you guys have any questions about the fuel system?
I do.
Yeah, go ahead.
Okay, so I don't understand, like, if the capacity is 26 gallons and the usable is 22.5, how do I know if I have 26 or 22.5? And like, how does that affect my weight and balance when I'm doing those calculations?
That's a great question. So, when we're talking about usable fuel, we're really talking about our legal limitations. So, for our day VFR flight, we need to have at least 30 minutes of fuel on board the aircraft at all times in order to be illegal. Same thing with at nighttime, it's 45 minutes. So, in that POH, they account for that and they say you have a 26-gallon fuel capacity. Right? That doesn't change, but they're saying theoretically only 22.5 of those gallons are usable due to your legal limitations. So when you're doing your calculations for weight and balance, you're just going to be using it based off of the 26-gallon total capacity, because just because you can't use it doesn't mean it isn't there. And how do you know if you have 22.5 or 26? It's the same way that you would know really how much you have any fuel. Is we're just going to do our performance calculation. So we're just going to know what our burn per hour is, how long we're going to be flying, and then we're just going to plan accordingly so that we never get down to that 22.5 range. Does that answer your question?
Yeah. Yep. Thank you.
Yeah, you're welcome. Any other clarifying questions? Okay. All right.
I'm sorry, I have a question.
Oh yeah, please.
I'm just mulling this over. I was even trying to look in my POH, but I fly a Cessna 172, and I know that the fuel is gravity fed. And I actually just was in the shop looking at the plane with the cowling off, and I can't remember, like, where is the fuel pump, or do I have one, and what does it look like? Is it engine driven? Is it electric? Sorry, I know that's not a plane you're featuring in this presentation, but I just thought I could ask.
Absolutely. So one thing I will say is it is going to depend on the type of 172 you're flying. Do you know kind of what year you're flying? Do you know if it's an older model or a newer model?
It's a Mike.
Okay. Perfect. So in that case, you are going to have that gravity-fed fuel system, same way, but you are going to have that engine-driven fuel pump. There won't be an electrical fuel pump. They did add that on like recent models for that redundancy feature that we were kind of talking about earlier. But it will be attached to your actual engine. And unfortunately, and unless you know exactly what you're looking for, it's not going to be easily identifiable. I would pull up a picture right now, but the thing about Google is that unless, like, you can't really trust, like, if I type in Cessna 172 fuel pump, it may pull up something that really isn't a Cessna 172 fuel pump, and I don't want to show you something that is in fact incorrect. But I'd be more than happy to, like, after this session closes, like, if I could, I'll get your phone number and then I can actually take a picture of either the 150's fuel pump or find a 172 fuel pump that is, vouched for and accurate, and send it to you so you know what you're looking for next time you're in the shop.
Yeah, thank you. I'll make sure you get my number in the chat, and I appreciate you answering that. I'm just going to keep looking at my POH too. So thank you.
Oh yeah, you're totally welcome. And yeah, for 172 mic model, it's definitely that gravity fed and engine driven. So just to clarify with that, even if you have a gravity fed fuel system, you're never gonna not have a fuel pump at all. There will always be a fuel pump in play, whether it's electric, engine, or both.
Okay, that answers my question. Thank you.
Oh yeah, you're very welcome. Okay. I'm going to move on. If there is anything else, though, you guys, again, just jump on in. Don't feel bad about interrupting me. I just can't see the Zoom while I'm presenting. So, okay. So in the same vein of airframe, we're going to talk about electrical pretty briefly. So electrical can be somewhat complex. There's a reason I didn't put the diagrams in there, is sometimes it's a little overwhelming to look at if you don't know what you're looking at. But both of the POHs, the Cherokee and the 150, have those diagrams available. And I would recommend taking a look at them. If they don't make 100% sense, it's okay. They're a little bit convoluted. So I'm going to try and target some main features of the electrical system. So in the 150, we have a 14-volt alternator and a 12-volt battery. And that's actually the same in the 140. So I do have a question, is, do you guys have any guesses as to why we would want a 14-volt alternator if we have a 12-volt battery? Why wouldn't we just make them both 12 volts?
Maybe to ensure that we're always having power going to that battery and we always have power.
Exactly that. So if we had a 12-volt alternator and a 12-volt battery, they may just kind of cancel each other out because they're both operating with the same amount of power. One can't really feed off the other. So if we're always having a slight overcharge per se from that alternator, we're always making sure we're actually charging the battery and not just borderline maintaining it. Because also it's really hard to charge something with equal power. It doesn't really work out that way. One thing I will point out, though, is that when we're overcharging something, that sounds inherently like, oh, wouldn't we be worried about overcharging the battery? Yes, we would. That's why they installed something called the voltage regulator. Exactly what its name sounds like, regulates the voltage from the alternator to the battery to make sure we're always maintaining it at peak power, but never overcharging it. And that's the same in both the Cessna and the Piper. And some things that are electrical system powers, again, pretty similar between the Piper and the Cessna, but there are a few key differences. So in our Cessna, our battery is going to power our radios and our navigational equipment. It's going to power our lights. Our battery will power our starter. So if you've ever tried to start a plane on a cold morning and it just kind of won't, the starter kind of just won't click over, it could be because on that cold night, your battery lost enough power to where it can't power that starter to get you started, because the alternator is only running when the engine's on. So if you've ever taken a look at an alternator on an airplane or an alternator on a car, they work, almost identically. When the engine's turning, the alternator is turning. But before that, we're just relying on the battery. So if you ever are out in pre-flighting and you get distracted by, I don't know, your mom giving you a call and you leave the nav lights on, there's a good chance that you are going to kill the battery, because just like with your car, the engine's not on, so the battery can't recharge. And in the Cessna, it also powers our flaps. And that's a kind of key difference between Bluebell and the 140, is that In the 140, we have something called a Johnson bar, which is that mechanical linkage that is going to extract our flaps. So power or no power, we have flaps. But in the 150, if we were to ever have an electrical problem for some reason, we are also going to kind of run that risk of not having the ability to extend or retract our flaps. So that's definitely something to be cognizant of. And I'm sure that at some point, for those of you flying the 150 or even the 140, your CFIs will do landings with you that are no flap. And what that means is being able to manage your energy and come into land when you don't have access to your, basically your air brakes is what flaps are. So if we ever had a problem in the 150, you'd be well equipped to say, hey, I've practiced these before. I know how to come in and manage my energy and land without flaps. So that's kind of just one of those quirks with the 150. And in both of these aircraft, we have our fuses and buses, and more commonly referred to as circuit breakers, which is what these are here on the right, the bottom right. And I'm sure you've seen them in both of those aircraft. And those are sending selected power to each of those systems. So, for example, there may be a circuit breaker for the strobe lights specifically. So you may have just, very well good charge from that alternator, good power from that battery, and you pop that strobe circuit breaker, you don't have strobes anymore because you are choosing specifically to cut power off to that one piece of the system. And there's a few reasons that can be helpful. Is number one, we don't want everything connected to each other because if one thing fails, it may cause the entire system to fail. And in the case of an airplane, that doesn't bode so well for safety. So when designing an aircraft, they specifically kind of diced things up so that if everything wasn't interconnected, so that if you had a strobe light, you also wouldn't have an entire navigational system failure. The other reason that can be helpful is that if you had an electrical fire, which is pretty uncommon, and I mean, by pretty uncommon, I mean, I don't know the last time I heard of anybody having an electrical fire, but if you were to have an electrical fire, again, you don't want everything connected because if your strobe lights are on fire, you don't want your entire radio system to start, catching flame. So if you turn everything off and isolate that system the way that the designers plan for you to be able to do, then you're able to mitigate and isolate risk. Let's see here. And with the 140, we've got the same setup here as far as our 14-volt alternator, 12-volt battery, radios and navigational equipment, still powered by electrical system, lights and starter again just being the battery. But our biggest differentiation here is that one, we don't have to rely on the electrical system for our flaps, and two, we do have to consider that electrical fuel pump. So if we had an electrical failure, we also have to consider what's that going to mean for our electrical fuel pump. Now, again, redundancy is great. We've got that engine-driven fuel pump. So if we did have an electrical failure, we're not going to have an engine failure, which is good because that wouldn't make any sense. But you want to consider that if you were having some type of electrical problem, you want to think, okay, I also got to consider, I'm not going to try and do a 60-degree bank turn here because my fuels might start sloshing all over the place and then I'm going to have a bigger problem. So those are just kind of the quirks between the two aircraft. But overall, your electrical system is pretty straightforward, besides those diagrams, which are kind of a little heinous in all honesty, but worth taking a look at nonetheless. Does anyone have any questions about the electrical system? I know I didn't get super in depth with that. Again, it's just because I don't want to overwhelm you all with like a huge amount of in-depth information. Okay. All right. Let's move on to the instruments, which could be really an entire lesson on its own, but I'm going to try and highlight some some main points here. So in our flight instrument system, we have three main systems, I guess you could say, at work. And that's going to be our vacuum system, our electrical system, and our pitot-static system. So for the vacuum system, we have two instruments, which is our false horizon or our attitude indicator, which is going to be that blue above brown, little slingshot looking guy over here, and our head indicators. Compass, which is center on the dash, but our actual heading indicator, part of our 6-pack. And when I say vacuum driven, what I mean is vacuum pump. So attached to our engine is a vacuum pump. They call it the engine driven vacuum pump, which, makes sense. And the vacuum pump does exactly what it sounds like it does. It creates a vacuum in these two instruments. And the reason it does that is to spin these gyros. We have both of these instruments here, along with the turn coordinator, which we'll get to in a minute, are gyroscopic instruments. So, and they're vacuum powered. So inside this little sealed case here, and I don't know if any of you have ever actually seen a flight instrument out of the panel, but it actually does look like this. It's a little cylindrical tube. It's not just a little face of an instrument. It goes back 6-7 inches to house, the gyro and the gimbal and the whole setup. So it's interesting to see if you ever are in a shop to kind of look at that. So inside of the case, that's what they call it, that little cylindrical tube there. Inside the case is a gyro. And what that gyro is doing is sensing our position. So I don't know if you've ever spun a little top, right? Or even a coin. That's essentially what the gyro is doing. And when you spin that top, not so much the coin, but when you spin the top, you can kind of press on either side of it. Press it ahead, press it to the side, and it won't typically fall over. That's because of something called rigidity in space. So these gyros are rigid, and now they're not going to fall over anyway because they're, designed in a way to not fall over. But the way it senses your movement is because when you bank the aircraft, right, so you enter a turn, or when you pitch the aircraft, so a climb or a descent, it's essentially like pushing on the gyro. So you're pushing ahead, behind, on the side of, and that gyro is feeling that movement. So it'll move, it'll kind of move with you. And there's some arms down here attached to the gyro that move the aircraft on the face, which is what you're seeing in the cockpit of the instrument, which will tell you your relative position to the false horizon. So 30 degrees of bank and 10 degrees of nose up, or whatever you're doing. And the reason that it's vacuum powered is because in order to spin the gyros, which this whole system wouldn't work, because if you, again, with the top's just sitting there, it's not spinning, and you push it, it's not going to really do anything. It's the whole spinning ideal that gets you to have that rigidity in space and gives you the indication that you're looking for. But the gyro can't spin without the air from the engine-driven vacuum pump. And I know I was talking specifically here about the attitude indicator. But it is the same thing with the heading indicator, except for the heading indicator doesn't give you pitch. It only gives you roll, essentially. So it's rolling the degrees of the compass. Does that make sense? Is there any questions about the vacuum-driven engine pump or engine-driven vacuum pump? Okay. So with the electrical system, oh, actually, one last thing here is with the suction gauge. When you're doing your run up and you go to 17, 1800 RPMs, which depending on the plane that you're flying, and you are doing your magnetos check or you're pulling to idle, another thing you're looking at is your suction pump or your suction gauge. And your suction is telling you whether you're getting enough power or enough vacuum from your vacuum pump to power your flight instruments. So don't just kind of look on that one by the wayside and forget that in your kind of like run up scan. Take a good look at it and see, is it indicating in the green? Has it been indicating at all? Because if not, you may have a faulty vacuum pump, which in VFR conditions is not detrimental, but does affect two of your instruments. So kind of like to have it. And with our turn coordinator, it's really it's kind of the same setup. As you can see in here, we also have a gyro inside of our turn coordinator. The biggest difference is going to be where it's getting its power from. So you can kind of notice that the gyro inside of the turn coordinator looks a little bit different from the gyro inside of the attitude indicator or the heading indicator. The inside those two look pretty identical. And the reason for that is because instead of being vacuum driven, it's actually electrically powered. So if they're all gyros and they're all kind of sensing the same realm of movement, why would we make two vacuum and one electrical? Do you guys have any guesses? It's because of redundancy. Aircraft designers love to be redundant, and we love them for it because it makes our lives a little safer. The reason that they don't just make them all vacuum powered is because they kind of all do serve the same purpose. Now, not identically, of course, there's some you'd rather have over others, but if you were to have a vacuum pump failure and you lost your ability to know if you were turning based on your attitude or heading indicator, well, you still have that turn coordinator because it's powered electrically. And vice versa. If you were to lose your electrical system and you lose your ability to, have your slip skid indicator, so your ball, your coordination, or your 2-minute turn, so telling you your rate of turn, then you still have the ability to have some of that information from your vacuum powered instruments. So that's really why we have those two different systems there. But short as I can be, short and sweet, those are our three gyroscopic instruments. So yeah. Before I move on to pedostatic, which is our last section, and I would say honestly is probably kind of our heaviest hitter, as it has a little bit to it. Do you have any questions about any of the other rest of the presentation? Alrighty. Okay, so our pedostatic instruments. Those are going to be our three remaining instruments, other than the three we just talked about, which is going to be our airspeed indicator, our vertical speed indicator, and our altimeter. So when we say pedostatic, what do we mean? Well, we mean our pedo tube and our static port. Now, that's the case in the 150, where we have those two separate areas to get that information, pedo tube, static port. But on the Cherokee, we actually have something called a pitot mast, which is this right here. You've probably seen it if you've pre-flighted the Cherokee. And that gets both our, it serves both as our pitot tube and our static port. So it's one place for all. And that's just an aircraft like designer quirk. So most Cessna products are going to have the two separate. Most Piper products are going to have the one, that pitot mast. So when we talk about pitot-static, sometimes it can be a little confusing because we say the pitot-static system as a whole, which kind of leads you to believe that both or well, all three of those instruments are relying on both pitot tube and the static port, but that's actually not the case. Only one instrument relies on both the pitot tube and the static port. And do any of you know which instrument that is?
The airspeed indicator?
That is correct. It is the airspeed indicator. So the airspeed indicator gets information from both our pitot tube and our static port. What does it do with that information? What does that information do for us? Well, when we are moving through the air, right? Like we are an aircraft moving through the air. That's called dynamic air. That is the airspeed that we are picking up by being a moving object through the air. So essentially kind of the same as like your speedometer in your car, right? Your car is moving through the air. That's the speed we're measuring. But the difference is that we're also moving up and down. And when we move up in altitude, do you know what happens to the air molecules, like when you go up in altitude?
They get thinner.
They get thinner. That's exactly right. So because of that, if we didn't also measure against the static air, which we'll get to in a minute, we wouldn't have an accurate reading. So that's why we use both the pitot and the static port. So we have ourselves as the aircraft moving through the air. That's called dynamic air. We also have the ambient air around us. So when I say ambient air, I mean the air sitting as it is undisturbed at the, whatever pressure we're at, altitude, so on and so forth. Ambient, right? That is measured through the static port. That has nothing really to do with our speed. It really just has to do with the air surrounding us. So what the airspeed indicator does is it measures those two pressures against each other, the dynamic and the static. So I have a little another cutout of a cake here for you. And you can see here something that kind of looks like a gong. I don't know, in my opinion, like this little case here, little gold wafer. And inside of that, this is called a diaphragm, by the way, diaphragm. That is where our dynamic air goes into the diaphragm. Our static air, on the other hand, is fed into the case of the airspeed indicator. That's how they're measured against each other. So we have our dynamic air, right? Speed moving through the air, and the static air. So as you said earlier, when you go up in altitude, the air gets thinner, right? And what that does is causes less air molecules to be inside of the case. That causes less pressure to be on the diaphragm, which causes it to expand. This also happens when we go faster. So if we're moving objectively faster through the air, we have a stronger air pressure inside of the diaphragm, causing it to expand, which causes it to show a higher airspeed reading on the airspeed indicator. Now, vice versa, you slow down, you have less air pressure inside of that diaphragm. Makes sense. We're not moving as quickly, not as much air is entering through that pitot tube, molecule-wise, which is going to cause a lower reading on the airspeed indicator. Now, something that can happen more with the 172 than with the Cherokee is if we're in a certain configuration, such as a side slip, which for those of you who may have not done that before, it's where you have kind of opposite aileron. So if you're turning your aileron towards the right, you're putting your rudder into the left. And this kind of causes you to almost drift. Like if you think about like a car, like if you've ever seen like Fast and Furious and they drift, you know, it's kind of like doing that through the air, which can cause a disruption of the flow of air into the pitot tube, which can kind of sometimes disrupt your reading a little bit. Now, nothing disastrous by any means, but that's one of the kind of the quirks of the airspeed indicator. And that's kind of our big instrument. Now, there is I will say, there's a bit more to the airspeed indicator than we're going to talk about today, but I want you to understand essentially where it's getting its information from, and then how that information is useful to us in the airplane. Is there any questions about the airspeed indicator? Okay. Let's talk about the vertical speed indicator. Now, the vertical speed indicator has the same setup as the airspeed indicator, except for instead of using pitot and static, it's actually using static and static. So you might think, well, how is it getting information by measuring static against static? Well, how it's doing that is similar to how the airspeed indicator is measuring pitot against static. Inside, it has a diaphragm. It also has a line to the case. So in the VSI, we have two different separate lines coming from the static port. One feeding into that diaphragm and one feeding into the case. And in this situation, again, what we're measuring is really a pressure differential. So both of these instruments are wanting to find an equilibrium, right? They're wanting to, the diaphragm wants to be at rest. It doesn't want to expand or contract, but it's trying to equalize the air between the case and the diaphragm, molecule-wise, pressure-wise, by expanding and contracting, which is going to give us those movements. So we have a direct line to the diaphragm. That means it's unimpeded as soon as we move up in altitude, which means less dense air, or down in altitude, which means denser air. The diaphragm is getting that change in density immediately. Now, there's another line going to the case, but it has something called calibrated leak or metered flow, whatever makes more sense to you. It's kind of like a toll bridge, at the line to the case, where it has to meter it in rather than getting direct flow. The reason for that is to cause a pressure differential. So, for example, let's say we're going up in altitude, right? So less dense air. Well, we go up, that diaphragm immediately feels that less dense air. However, since we don't have immediate change in the case, we momentarily have denser air in the case than we do in the diaphragm. Well, what do you think that does? It compresses the diaphragm. And that's why we also sometimes say that the VSI has a lag, which it does, because it's built to be that way. It's built to have a calibrated leak, which means it's metering in that change in air so that you can cause that pressure differential and show that climb, right? So we're climbing less dense air in the diaphragm, momentarily denser air in the case shows, say, a 500-foot, per minute climb. Now, when you level off from that climb, there's no more change in air density or air pressure, right? Because we've leveled off. And so it will, after, about 7 seconds of lag, it will equalize. Now we have the same pressure in the case as we do as the diaphragm, which will then show a 0 foot per minute climb. Does that make somewhat of sense to y'all?
Yes, thank you.
Okay, you're welcome. Okay, one last instrument. We're in the tail end here. Is the altimeter. So, last instrument of the pedostatic system, and it is set up. It's set up pretty similarly to the airspeed and the vertical speed indicator, but it is definitively different. So I have on the side here a picture of something that looks like a diaphragm, but it's actually called a sealed aneroid wafer. And if you've ever seen one of these in person, which I kind of doubt you have because I haven't either, I've only seen a picture, they actually kind of look like wafers, which has kind of permanently ingrained that vision in my mind. Is whenever I see these things anymore, the altimeter, I always think the Nilla wafers. So because that's what they look like in there. But the sealed aneroid wafer functions essentially the same as a diaphragm, except for one key difference. While the airspeed and the vertical speed have sent information directly to the diaphragm, which has caused it to expand and contract, the sealed aneroid wafer, as the name implies, sealed is sealed. So there's no information going directly to that wafer. Now, what is inside of that wafer is sealed sea level pressure. Does anybody know what if you were listening to the weather, the altimeter, what would the altimeter setting be on a standard day?
29.92.
That's correct, 29.92. So inside of that wafer, we essentially have sealed 29.92, which is a standard day at sea level. Now, why would we want that? Well, it's an altimeter. We want it to know when we're at essentially mean sea level 0 feet, right? Because that's how we're going to get our mean sea level for every other altitude that we're climbing to. I was going to say or descending to, but hopefully you're not descending below 0 feet, because then we would have a. So inside there, we have that sealed 2992. Now, like the other instruments, we also have a line going to the case from our static port. So as we go up in altitude, or we go down in altitude, our air density is going to change. And it's going to be measured against our sealed sea level pressure. So if you took off out of McClellan, and off the top of anyone's head, does anyone know what the airport elevation is at McClellan?
It's 77.
77? Wonderful. Okay. So you take off out of McClellan and your altimeter reading 77, right? Well, you're pretty close to sea level. So you're starting off on a pretty good playing field there. And we climb up to our traffic pattern altitude of 1,100 feet, right? 1,100. Well, as we go up in altitude, even at 1,100 feet, we're getting slightly less dense air. And that's causing less of a resistance on our sealed sea level pressure, right? Because essentially, that sea level pressure on a standard day is going to be the densest air we're going to experience because it's sea level. So as we go up in altitude, it's going to be less resistance in the case, right? Because we get less dense air, which is going to cause that wafer to expand, which is going to move the dials on the face, indicating our altitude. But how many times really have we flown on a day where the altimeter reads 2992? Not that frequently, unless you're lucky and you're like picking your days really well. But most of the time, it is a non-standard barometric pressure. So what do we do then? Are we just going to get an erroneous reading from our altimeter? No. We have what's called the Colesman window, which I tried to kind of like zoom in over here. And that's when we have our little dial, usually like on the left side of the altimeter, and we listen to the altimeter. It tells us, oh, it's 3001. Well, we dial it on to 3001. What's that doing? Well, it is calibrating our wafer to tell us 3001 is our standard day now. Not 290902. We want you to measure against 3001. And that's remember, it calibrates it like that. And it's got that little dial on the top, you see? I don't know if you can really see, but it's like at the top of that little wafer. And it dials it in. And now you've set your barometric pressure that you want to be measured against. Because really, most times we're not going to be operating in a standard day. Now, one thing that's really important about our altimeter, and some of you may have experienced this, some of you may not have, depending on where you're kind of at in your training, is when we fly cross country, our barometric pressure will change. So our barometric pressure at McClellan may be 3001, but then we fly up to Chico and suddenly it's 3019. Well, that's a big difference, right? It's almost, it's like almost 20 degrees of difference, like 18 degrees. If we don't reset our altimeter setting, our little Colesman window, right, we're going to have a highly inaccurate altitude reading, which can be dangerous for us, dangerous for other people, and just, overall inconvenient. So if you're doing your cross-country flights or even flying one airport to the next, you always want to get that weather, not just because, you want to make sure you're not in a 12-knot gusting crosswind, but also because you want to make sure you're operating on the most recent altimeter setting, because it can vary even airport to airport. If you went from McClellan to Mather, which is a short, 8 miles away, we could have a slightly different barometric pressure. So you want to make sure that you are always being vigilant about that. And I also included kind of the altimeter strip on a G5 for any of you that fly glass systems. We have that on the side here, which it functions essentially the same. The way that it gets this information is different, but that's an entirely other ordeal. But that's how it looks. So it will kind of show you it in a vertical model rather than a radial model. So, and you can set your altitude bug. So you can say, I want to climb to 8,000, and it will tell you when you're nearing that altitude, which is a nifty little feature. So yeah, those are our pitot static instruments. Does anyone have any questions about anything we've talked about today? I know it was kind of a lot, so sorry, didn't mean to info dump.
I asked all my questions.
Well, thank you. Thank you all for participating today and for being such a great audience. I really appreciate it on my first time. If there is anything else that you need or any other clarifying questions you think of after this, I can post my phone number in the chat if any of you would like it. And I can also send you that 172 fuel pump as well.
Thank you so much, Mia. Welcome to Girls Love to Fly.
Thank you so much. I really appreciate it, you all.
This was awesome. Thank you, the Gavins.
Thank you. I just put my phone number because I am very curious. Because I even just saw in the POH, I was looking at the fuel system drawing in my POH, and it doesn't show the fuel pump anywhere. So now I'm extra confused.
That's one of the quirks about Cessna is it won't show the fuel pump in the fuel system. So I totally relate. I will I'll text you in the next 5 minutes and we'll get it sorted because I feel your pain.
Okay, thank you so much.
You're welcome. All right. I hope you all have a great night and thank you again.